This video contains the solutions for 7-6 multiple choice practice and also one free response question that we went over in class, but I thought I'd put it in a video also so you had it to refer to. Okay, number one, average value of the square root of x over the interval 0 to 2. So that would be 1 over the interval is 2 wide times the integral from 0 to 2 of x to the 1/2 dx. That's the average value. So evaluating that, the antiderivative of x to the 1/2 is x to the 3/2 times 2/3 times the 1/2 that's already there from 0 to 2. And the 2's cancel out, so it's 1/3 times 2 cubed is 8. And the square root of that would be square root of 8, which is 2 square roots of 2. So that looks like answer choice C. Number 2, average value of this from 0 to 2. So again, that's going to be 1/2 times the integral from 0 to 2 of this x squared times the square root of x cubed plus 1 dx. And that looks like a u substitution. Let's let u equal x cubed plus 1. And du would be 3x squared dx. I've got my 3x squared, so I need the 3 in here, which means I need a 1/3 out here. So that turns into 1/6 times the integral. My new limits here, plugging the 0 in here, would be from 1 to, plugging the 2 in here, 2 cubed is 8 plus 1 is 9. And then all of this turns into the square root of u du. That's u to the 1/2 du. And we just did that antiderivative, so that's 1/6 times that antiderivative is 2/3 u to the 3/2 from 1 to 9. And that's the 2 and the 6 cancel out, leaving a 3 down there, so that's 1/9. And then 9 to the 3/2, that's the square root of 9, which is 3 cubed is 27, minus 1 to the 3/2 is 1. It's 26 over 9, which is A. Number 3. It's the average value of y, or in other words, the average value of the function, right? Y value, same thing, of the part of the curve, this, which is in the first quadrant. Well, let's see. If we think about what the graph of that's an upside-down parabola with zeros at 0 and 3. So we're talking about from 0 to 3. You can sketch that to confirm that if you like. So we're talking about 1/3, 0 to 3, right? The interval is 3 wide, so we're dividing by 3. 3x minus x squared dx. That's 1/3. Antiderivative of that is 3x squared over 2 minus x cubed over 3 from 0 to 3. And that's equal to 1/3 times 3 times 3 squared is 27 over 2. 27 divided by 3 is 9. And if we wrote that in halves, that'd be 18/2. So 27/2 minus 18/2 is 9/2. That's 1/3 times 9/2. That simplifies to 3/2, which is C. Average value of 1 over x on the interval from 0 to 3. That interval is too wide. Antiderivative, that is natural log x. Don't need absolute value signs because they're both positive. And that's 1/2 times the natural log of 3 minus the natural log of 1. But the natural log of 1 is 0, so it's 1/2 natural log 3, or d. And last, if the derivative of something is 1 over x, then the average rate of change, so in other words, the average value of the rate of change, so that's the average value of this from 1 to 4. Remember, we always have to pay attention to what they want the average of, the average rate of change, and this is the rate of change, or the derivative. And that's going to play out just like this one. That's 3 wide. So we want 1/3 of that, so it's 1/3 times natural log 4 minus natural log 1, but natural log of 1 is 0. Now if you look here, it doesn't match up to any of these, so let's see if there's any logarithm tricks we can do. 4 is 2 squared. So if we wrote it like that and then said, oh hey, I can take that out to the front, that would be 2/3 natural log 2. So that's the same as c. All right. Now, let's take a look at this. Maybe we'll look at a different one in class, since I'm going to do this one for you here. Blood vessel is 360 millimeters long, with circular cross sections of varying diameter. Table above gives measurements of the diameter of the blood vessel at selected points along the length of the blood vessel, where x is the distance from one end of the blood vessel, and bx is a twice differentiable function, so that means we can do any calculus we want, basically, that represents the diameter at that point. All right. So, write an integral expression in terms of bx that represents the average radius in millimeters of the blood vessel between 0 and 360. So we want the average radius in millimeters. Okay, my b of x function is the diameter. So b of x over 2, since this is the diameter, if we divide those by 2, that would be the radius, right? So we want the average of this, of the blood vessel between 0 and 360. Well, from 0 to 360, so that's going to look like this. The average value, the interval is from 0 to 360, right? We want the average value, so I have to divide by how wide the interval is. And then I want the average value of the radius, which would be x over 2 dx. So there's the integral expression, the average value of the radius. We had to cut that in half because they gave us diameters. All right, part B, they want us to approximate the value of your answer from part A using the data from the table in a midpoint Riemann sum with 3 subintervals of equal length. So let's see, 3 subintervals would be 1, 2, 3, and they want midpoint rectangles. So let's see if we can find that. So let's see, the first rectangle is, oh, and by the way, we're still doing the 1 over 360, right, because we're approximating this. So, and I'm also going to, this 1/2 here, I'm going to pull that to the outside so I can just deal with the b function. All right, now let's get the area of these three rectangles. The first rectangle is 120 wide times the midpoint value is 30, plus the second rectangle, they're all equally spaced, it's all also 120 wide, and it's also 30 is the midpoint value, plus 120 wide times 24. And I suppose we could use our calculator for that. Or maybe we can, well, let's see if we can simplify it. So I've got 120, 360 times 2. If I factor out the 120s with the 360, there's a 3 here, right? 120 goes into 360 3 times. And then if I factor 2, if I multiply the 2 through, that would make these numbers a little bit easier to deal with. 1/2 of this is 15, 15, 12. This is calculator allowed, so you don't have to do this. My calculator's not on, so I'm being lazy in a way, I suppose. So this is 1/3. 15 plus 15 is 30. So that's 42. It's 42, which is 14. And they told us that it's in millimeters, but of course we could have figured that out. This is the average radius, so that's a measurement of length in whatever units are in the problem, so it'd be 14 millimeters. Part C, using correct units, explain the meaning of this integral in terms of the blood vessel. Now let's take a look. That looks like pi times, well, that's the diameter over 2, that's the radius, so pi r squared. Well, all the integrals that we've been doing recently, when we take the integral of something and we do pi r squared, that's a volume, right? So if you think about this, this is like adding up all of the little slices, right? So that would give us volume, right? It would give us the volume of the blood vessel. Pi r squared gives us the volume from 127 to 275. So it would be the volume of the blood vessel from 125 millimeters to 275 millimeters. And what would the units be? Well, it's a volume, and since all our distances are measured in millimeters, the units would be cubic millimeters. And then last, explain why there must be at least one value between 0 and 360 where the second derivative is 0. Well, let's see. If we find, let's look at average slopes. What's the average slope from here to here? So the average slope let's think about this for a second, actually. So let's look at this here. Here, from 0 to 60, the diameter is increasing, right? From 24 to 30, and then it's decreasing, and then increasing, and then decreasing, and decreasing, and increasing again, right? So the b prime of x goes from 0, if we made like a number line like this, 0 to 60 to 120, for example. I don't think we have to go further than that. it's increasing and then decreasing, right? I mean, it might not be the whole time, but for at least part of the time, it's got to be increasing from here to here and decreasing from here to here, because it's twice differentiable. That means everything's happening smoothly. And if it's going from increasing to decreasing, does that mean that there has to be an inflection point between those two? I think it doesn't, but actually maybe this is where we should be looking. Look at that. There's two places where the average slope is 0, so maybe that's where we should be looking. So average slope from 60 to 180 is 0, and the average slope from 240 to 360 is 0. Now, the mean value theorem says the average slope has to be attained by the function, so that means there is a point in here where the derivative is 0, and also there is a point in here where the derivative is 0 by the mean value theorem. And look, if there's two places where the derivative has to be 0, that means that between these 2 points, the average rate of change of the slope, in other words, if we took the slope between those 2 points on the derivative, in other words, the average of the second derivative, is 0. And then again, by the mean value theorem, there must be a c in between. Let's see, what's that? Somewhere between the very beginning of where we were looking at, somewhere between 60 and 360. Where the second derivative is 0. That's pretty tricky. That's like a double mean value theorem to get there. And that's not a totally typical part of a problem like this, but usually if they're looking for a place where explain why there must be one of these where a derivative or second derivative, that really stinks of mean value theorem. And probably just mentioning the mean value theorem somewhere gets you a point out of that, and we'll have to check the rubric. All right.